In the previous video, we saw a very common example of a linear voltage regulator, but more specifically, we learned about one of the most common problems that arise when implementing linear regulators. Luckily, we have a solution: the switch mode regulators. Unlike a linear regulator, where the output is basically variable resistance, and for this reason we have such poor efficiency, in a switch mode regulator we use a different technique: PWM. With the PWM technique, instead of working with a transistor at a gain lower than saturation, we are working with a transistor with minimal resistance, and therefore the energy loss in the form of heat is much lower this way. How do we achieve a stable voltage output by using PWM? By using a low-pass filter. In these cases, we use an inductor and a capacitor. The effective voltage of a PWM output is calculated by the peak voltage times the duty cycle. For example, if a PWM signal has a peak value of 12 volts and the duty cycle is 50%, then our effective voltage is 6 volts. This way, instead of the dissipated power being determined by the input voltage minus the output voltage, we now only consider the transistor drop. This implies extremely superior efficiency. Today, we will then take a look at a very popular compact switch mode regulator model, the LM2596 series. This is a high-frequency switch mode regulator, 150 kHz, which operates with very few components, and also provides the option of fixed outputs and variable output. We have an input of up to 40 volts, fixed outputs of 3.3, 5, and 12 volts, and an adjustable range from 1.2 volts to 37 volts. We also have a maximum current of up to 3 amps. The regulator, both in the TO220 through-hole and TO263 SMD presentations, has 5 pins, which serve the following functions. Bin, this is the pin corresponding to the input voltage. Output, this is the pin corresponding to the output. Ground, this is the pin corresponding to 0 volts or ground. Feedback, this is the pin corresponding to the feedback. Here it is connected to the output when it is fixed mode, or to the resistor divider arrangement when it is a variable output. On-off, this is the pin corresponding to the external digital on-off control. It turns on when the pin is brought to 0 volts and turns off when a voltage greater than 1.3 volts is applied. Now we have the internal structure, which we can see is much more complex than a linear regulator. But the operating mode is summarized as follows. We have an internal reference of 1.235 volts, which goes to a comparator that works together with the feedback. This signal then goes to another comparator that works with a 150 kHz sawtooth signal. This way we obtain an output of PWM. The comparator output goes to 0 volts when the reference is higher than the amplitude scaling of the sawtooth signal. It then goes to a latch, which is controlled by 2 other comparators that work as current controllers. Then we have the driver of the NPN transistors, along with the thermal limiter, and finally the 3 NPN transistors in parallel that gives us the output. Now let's look at the usual operating mode. As we mentioned, we have both the option of a variable output and fixed output. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In PrismaSem Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. For the case of fixed output, we have this simple topology. We can see that we only need a Schottky diode, an inductor, and a capacitor. The selection of the Schottky diode is very simple, as we only select it based on the appropriate current and breakdown voltage values. But for the case of the inductor and capacitor, they are not precisely so simple. The datasheet offers a reference for the selection of output capacitor and inductance based on the output voltage, input voltage, and current. It is ideal to use this reference to obtain the best output performance. But if we don't have a critical application, we can go with the conventional values of a 33 microhertz inductor and 220 microfarad capacitor. But we must select the appropriate current value for the inductor for the output, preferably above the limit, for example 3.5 amps. And for the case of the output capacitor, select tantalum capacitors, since low SR capacitors are required for this case. So we have a very simple operation. For the case of variable output, we simply use a divider array consisting of two resistors. The output voltage formula appears on the screen, where Vref is equivalent to 1.23 volts and R1 is a fixed value of 1K, as recommended by the manufacturer. We then need to obtain the necessary value of R2, which is done with the formula shown on the screen. If we want a 7 volt output value, applying the values in the formula, we obtain the following. R2 equals to 4691 ohms. Now, this value can be relatively easy to obtain using a potentiometer, but not so much using individual resistors. So, in case of resistors needed to be used, we will have to select multiple values to obtain this total value in series. We will need a 4K resistor, a 690 ohm resistor, and a 1 ohm resistor to obtain this value. Well, now that we have seen the general operating parameters, it's time to delve into the datasheet. First, we have the operating conditions. Here it indicates a minimum input voltage of 4.5 volts and a maximum voltage of 40 volts. Also, a minimum operating temperature of -40 degrees Celsius and a maximum of 125 degrees Celsius. For the case of electrical characteristics, we have those established by the 3.3 volts, 5 volts and 12 volts outputs. We can see that there is a variation in the output between 200 millivolts and 300 millivolts for each case, and also a different efficiency. For 3 volts, we have an average efficiency of 73%, for 5 volts, we have an average efficiency of 80%, and for 12 volts, we have an efficiency of 90%. Subsequently, we have the shared electrical characteristics. First, we have the feedback bias current, which is between 10 to 100 nanoamps. Then the oscillator operating frequency ranging from 127 kHz to 173 kHz. The third parameter is VSAT or output saturation, which ranges from 1.16 volts to 1.5 volts. Multiplying this value by the output current, we obtain the dissipated power. For the duty cycle, we have the maximum turn-on value of 100% and turn-off at 0%. Subsequently, we have the current limit, which is set at a typical value of 3.6 amps and 6.9 amps. It is important to note that these are peak values and not stable values. Next, we have the consumption current value, which ranges from 5 to 10 milliamps. This also depends on whether we have feedback for the variable output, but it's a conventional value for regulators. After that, we have the output leakage, which is established at 50 microamps as a typical value. Then we have the quiescent current value but in standby mode, meaning when the regulator is turned off. Here values are set between 80 to 250 microamps, much friendlier values for battery applications. Alright, now that we have seen the datasheet conditions, let's verify these values in the laboratory. So here we have the operation of the PWM output before the low pass filter. We can see we have the duty cycle on the oscilloscope and we have a fixed output of 5 volts with the regulator. We are going to see that the lower the input voltage we have, the higher the duty cycle. And the higher the input voltage we have, the lower the duty cycle. This is obviously to compensate and have the fixed output of 5 volts, because the lower the input we have, the less of a reduction of the PWM duty cycle we need. So here we see how the PWM behaves. We have a very simple operation. Now we are up to 21 volts and we have a difficult with the trigger setup because there's a lot of jitter in the signal. But yeah, now we can see how it is getting lower and lower, and then we reduce the input voltage and we have a higher duty cycle. We go below and we get no response, obviously. We go up again and we have the normal operation. So here we have the operation of the regulator. We have a 5-volt output, an input of 20 volts, the output ripple, we have a 1 amp load, and we have the temperature measurement. We can measure that the regulator is around 34 degrees Celsius, which is pretty nice for the application, because with a linear regulator we will be getting above 70-80 degrees Celsius or even more without a heatsink. So we can see that we have a amazing performing efficiency in this case. Now the ripple is going to be something a bit nasty for some applications, but for example in this case that we only have resistive loads, that is not really a problem to be concerned about. Here we test again the temperature and we get 35-36 degrees, so everything is going nice. Now this regulator is not set up for high currents. The maximum is 3 amps continuously, but I wouldn't get the regulator to work up to 3 amps. I will get it to 2.5, 2.6 stops to leave room for some higher loads, transient loads or something else. But yeah, you shouldn't be getting this regulator up to 3 amps because you may be risking it a little bit. Well, it's time to draw a conclusion. As we could verify, the switch mode regulator offers a lot of advantages compared to using a linear regulator. Higher efficiency, no need or little need for a heatsink for the vast majority of cases, low cost, etc. But at the same time we have a few problems, such as increased noise, lower precision, presence of output ripple, and other issues. Like everything in electronics, each piece fits into different scenarios. For this case, these types of regulators are best used when handling considerable loads and when maximum efficiency is required. For precision applications, in most cases, it's not the best option.